The burning of magnesium ribbon is an experiment which demonstrates how magnesium ribbon reacts with the oxygen in the air to give magnesium oxide. Now let us check what exactly we are going to do in this experiment. First, take one magnesium ribbon and rub this with a sandpaper. Then with the help of tongs, burn this with the help of a candle or else burner. Now this ribbon will catch the fire, right? Then it will burn with a bright white color. Then we can observe the ash forming or else the powder forming also. This powder is nothing but magnesium oxide. So what exactly is happening here is magnesium, when we are burning in the presence of oxygen, we are getting magnesium oxide. Now if you check the balancing of this equation, here Mg is 1, here also Mg is 1, whereas oxygen are 2 atoms, but here oxygen is only 1 atom. So what I will do is, in front of this MgO, I will write 2. Now what changes were done, let us check once. 2 atoms of magnesium as well as 2 atoms of oxygen. Coming to the left side, here only magnesium is 1 atom, so I am keeping here 2 in front of it. So now I got 2 magnesium atoms and here also 2 oxygen atoms. So now left side, right side both balanced. Now here we collected the powder or nothing but magnesium oxide, right? Now how we are going to check this magnesium oxide nature, means it is acidic or basic. So first what we will do is take that magnesium oxide powder or else ash which we collected, dip it in water or mix with the water, and then take the litmus paper. First take the blue litmus paper and pour this water drops onto the blue litmus paper. We can observe that there is no change in that one. So from this we can say that it may be base or it may be neutral also. Now I am going with the red color. I am dipping this red color litmus paper into this MgO water. Now this red color will change to blue color. So red color is changing to blue color on litmus paper, means I can confirm that this is basic in nature. So magnesium oxide is a base. That's why when we are doing experiment on litmus paper, red litmus is changing to blue litmus. From this experiment, what kind of questions we can frame? The first question is, what is the color of the flame? When this magnesium oxide is being burned, flame is coming, right? So what is the color of that flame? That is white color. Next one, we got some powder kind of substance, right? When magnesium ribbon is burning, so what is that powder or ash? That is magnesium oxide. Next, here one reaction is happening. So what kind of reaction is this? Let us check once. Magnesium combining with oxygen and producing magnesium oxide. Here 2 elements or 2 compounds, that is A plus B, is combining to give single compound only. That I can write with some other alphabet, C. Okay, 2 compounds or 2 elements combining to give only one. So this kind of reaction is called as combination reaction. This is called as combination reaction. Okay, before doing the burning of the magnesium ribbon we are rubbing with the help of a sandpaper. Now the question comes, what is the purpose of rubbing with the sandpaper before burning the magnesium ribbon? Actually, whenever magnesium is exposed to the air, it will form a small or a thin layer of oxide, that is magnesium oxide. Normally any metal if you take, means based on the reactivity of it with the oxygen, it will form a small layer or the very thin layer of oxide on the top of it. So now to remove this already formed magnesium oxide layer from the top of the magnesium, it is necessary to rub it so that it will take a complete reaction. Now Magnesium is reacting with oxygen and we are getting magnesium oxide. Then in this reaction, heat is being released or heat is being absorbed. If you check that one, in this experiment to the reaction happen faster, that's why we are providing the fire. But in normal cases, magnesium, when it reacts with oxygen to give magnesium oxide, this is exothermic reaction. It means it releases heat. And don't compare this with our experiment right now, because in our experiment we don't have much time. So to do it faster, we are supplying the heat from outside, and so by looking at that one, don't confirm it as like endothermic. Actually it is exothermic only. Whenever magnesium reacts with oxygen, it produces magnesium oxide, which is exothermic in nature. It means releases heats. Now we will get a doubt. Magnesium we are burning in the oxygen and we are getting magnesium oxide. Now what happens? The same magnesium ribbon I am burning in a jar which has carbon dioxide. I repeat it. Magnesium we are burning in a jar or container which is filled completely with carbon dioxide only. Let us check what happens then. Magnesium reacts with that carbon dioxide which is filled in the container or jar and gives us magnesium oxide along with carbon. Now question comes again. Here we are discussing about the magnesium burning in the oxygen. Then are there any other metals which will burn in the presence of air besides this magnesium? Yes, so many are there. For example, iron. Iron reacts with the oxygen and gives us iron oxide, that is Fe2O3. The same way, sodium, another metal, also reacts with oxygen to gives us sodium oxide. One more, lithium. Lithium also reacts with oxygen to give lithium oxide. The next experiment is reaction of zinc granules with sulfuric acid. Actually, when zinc granules are reacting with sulfuric acid, Zn plus H2SO4. Here, zinc is more reactive than the hydrogen which is in sulfuric acid. So this zinc is going to replace this hydrogen. So it will form ZnSO4, and that replaced hydrogen will go and form hydrogen gas. So Zn plus H2SO4 gives ZnSO4 plus hydrogen gas. So what exactly we are going to observe in this experiment then? Zinc granules, whenever being added to sulfuric acid or whenever sulfuric acid is being added to zinc granules, we are going to get zinc sulfate and hydrogen gas. So here this is hydrogen gas, right? So gas, whenever it is being released, means definitely the bubbles will come first of all. Next, a metal is being added to the acid, so definitely it is exothermic reaction. It means temperature increases. Maybe this total quantity temperature increases, or else the test tube which we are doing in this experiment, the test tube also, if we touch it from the outside, it will increase its heat temperature. Now, okay, this is reacting, everything is going fine. How can we confirm that the released gas is the hydrogen gas? Now, Zn plus H2SO4 you added in a test tube, right? Now it starts giving bubbles by taking the reaction. Now bring one candle near to the mouth of the test tube. If you bring a candle near to the mouth of the test tube, by making the pop sound, the fire will put off. I repeat, by making the pop sound, the fire will put off. It indicates that hydrogen gas is present in that test tube. So it means zinc, whenever it's reacting with sulfuric acid, we are going to get zinc sulfate as well as hydrogen gas. Now, from the beginning onwards, we are discussing that zinc granules we are adding, zinc granules we are adding. So what exactly the zinc granules means then? Instead of zinc granules, is there any possibility of adding zinc in any other form? Let us check that once. Instead of zinc granules, I can add zinc lump also completely. So zinc lump, if we break it into pieces, we are going to get zinc granules. And the zinc granules, if we break it into pieces more, we are going to get zinc powder. Finest form. Okay, now What is the difference when we are adding zinc lump or zinc granules and zinc powder to the sulfuric acid? Zinc lump, it will be some kind of like this, right? And the zinc granules, the same, I'm making it into pieces, so it will be like this. Now still I am making this into powder form, so it will be like this one. Now if we observe the surface areas of all these things, this surface area is less, this surface area will be little more than the lump, and this surface area will be much more than these two previous cases. So whenever if a surface area of particular metal is increasing, obviously the reaction will be faster. So if we compare to the lump, if we add zinc granules, the reaction will be faster. When comparing to the zinc granules, if we add zinc powder, the reaction will be still more faster. To understand this one, for example, when I added a lump in the S2SO4 to form ZnSO4, let us assume that it is taking 5 minutes. When I am adding granules to form the same zinc sulfate, it will take hardly 2 minutes only. And instead of granules, if I add powder after reaction to get the zinc sulfate, I will take hardly less than 1 minute only. So as soon as the surface area is increasing, the reaction will be so faster. So obviously reaction is being faster means zinc sulfate will get faster, as well as the hydrogen gas also will be released faster than the previous cases. We are adding sulfuric acid. What happens instead of sulfuric acid if we add any other acid then? I am taking HCl then. Zn plus HCl gives rise. Now here also same again. This zinc is going to replace this hydrogen. So ZnCl2 we will form. ZnCl2 plus hydrogen gas will be released as usual. So when zinc reacts with the hydrochloric acid, it releases or produces zinc chloride. Along with that, hydrogen gas will be evolved. Now, what kind of reaction is this? Let us check them. In the previous one, sulfuric acid or else HCl, both are same. So, Zn plus H2SO4, we are getting ZnSO4 plus hydrogen gas, or else Zn plus HCl is giving rise to ZnCl2 plus hydrogen. Now here zinc is replacing the hydrogen, here also zinc is replacing the hydrogen. So this kind of reaction is called as displacement reaction. This is called as displacement reaction. And when this zinc is reacting with the sulfuric acid, or when zinc is reacting with the hydrochloric acid, we are being released with the heat. Heat is being released. So I can say that these two reactions along with the displacement reaction, those are exothermic reactions also. Exothermic reaction. So these two are displacement reactions as well as exothermic reaction. The next experiment which we are going to discuss is reaction of the lead nitrate, that is PbNO3 taken twice with potassium iodide Ki. Lead nitrate and potassium iodide. So what happens here is this lead goes and reacts with this iodine, so we will get lead iodide, and this K goes and reacts with NO3, so we are going to get potassium nitrate. So here lead nitrate is reacting with potassium iodide to form lead iodide and potassium nitrate. PbNO3 taken twice plus Ki gives rise PbI2 plus KNO3. Now, in the previous cases or here, we are saying that reaction is being done, reaction is being done, reaction is being done. Now, how can we confirm that a chemical change has occurred? This is a very, very important thing. How the chemical change occurred. How we are going to confirm that a chemical change has occurred. So, for this, what we are going to check is change in the state of matter, change in color, evolution of gas, and change in the temperature, formation of the precipitate, and smell change, that is order change. Let us discuss each of all these with one example. First, state of matter. How can we confirm a chemical change occurred? By looking at the state of the matter change. For example, I am taking ammonia, which is in the form of a gas. When it's reacted with the hydrochloric acid gas, we are going to get ammonium chloride, that is NH4Cl, which is a solid. Here gas reacting with a gas, and completely we are getting another state which is a solid. Now I can confirm that a chemical change occurred here. Next, how we are going to check? Just by looking at the color then. So previous case, that is lead nitrate PbNO3 taken twice reacting with Ki to gives us PbI2 plus KNO3. If you observe here, PbI2, which is formed after the reaction, it will be yellow in color, and the previous one, it is no color. So no color changing to yellow color. Now we can confirm that a chemical change occurred here. Next one is evolution of gas. Zinc granules, when we reacted with sulfuric acid, we are getting ZnSO4, and hydrogen gas is being evolved. Here hydrogen gas is released, so we can confirm that a chemical change occurred. The same equation we can use for temperature also. Zinc, when it's reacted with sulfuric acid along with the ZnSO4, H2 gas is being released, and here change of temperature will be there. The total test tube will be heated. Next one is precipitate. The same previous example we can give. Here yellow color PbI2 is forming, right? Actually this PbI2 is a precipitate. Next one, coming to the order change or smell change. Hydrogen gas, when it reacts with the sulfide, we are going to get hydrogen sulfide. Hydrogen, when it reacts with the sulfur, we are going to get hydrogen sulfide. We will get, it's a rotten egg smell. Magnesium reacting with oxygen to give magnesium oxide. Now this is a chemical equation, right? So every chemical equation has some limitations. So let us check the limitations of the chemical equations. The first limitation is we need to mention whether the taken reactants or the products are solids or gases or liquids or else any aqueous solution. Now in this example only, if I wrote just like it as magnesium plus oxygen gives us MgO, but in this equation it is not saying us that whether this magnesium is solid or a gas or a liquid, oxygen is a gas or else a liquid form, or else MgO is a solid or liquid or a gas. We are unable to get it from this just chemical equation. So always besides the elements we need to mention whether it is a solid or else a gas, or else a solid or else a gas. So this is one of the limitations. So the symbols below should be added to make it more informative. For example, solid means yes, liquid means L, gas means G or else upper arrow, or else aqueous solution is AQ. Like this we need to show compulsory. And the next thing is that whether this reaction is completed or it is incomplete, we couldn't able to find it out from the given equation. So this is one more limitation. Next one is how much time is being taken. This reaction is done in 5 minutes or 10 minutes or else whole day or else whole year is taking. We couldn't able to find out. So this is one limitation. Next one is what is the speed of it. We couldn't able to find out that also. In the previous case when we took this one, zinc lump, when it is reacted with sulfuric acid, zinc granules, when it is reacted with sulfuric acid, zinc powder, when it is reacted with sulfuric acid. For all three cases the right side part is same, that is ZnSO4 plus hydrogen gas. Now in any of these equations from the chemical equation it is not clear that what is the reaction speed. When we are taking a lump the reaction speed is slow, and when we are taking the granules little faster, when it is taking powder still it is more faster, but it is not being displayed in this equation. So this is also one of the limitations. Next one, the same example I am taking, zinc when we are adding to the sulfuric acid. Here this equation is not showing me which kind of acid we are adding, whether the added acid is concentrated or else diluted. So for that, before the acid name, I need to write whether it is diluted or else whether it is concentrated. And next thing is, it is not showing the temperature. This equation is being done means here we can feel the heat or hot of the test tube, right? And it means heat is being released, but in this equation it is not showing until and unless I write it separately. So the equation alone is not showing, and what is the pressure in the test tube, and what is the humidity present in the lab, and what is the catalyst we are keeping. So these all are not being displayed in the equation until and unless we show it separately. So these are some of the limitations. Let us check back again. The first one is, until and unless we show whether it is a solid or liquid or a gas, it is not being shown in the equation, and whether the chemical reaction is done completely or it's done half only, we get to know from the given equation. And what is the reaction time, what is the reaction speed is not shown in the equation, and whether the acids taken or diluted or concentrated is not shown, and what is the temperature present, or what is the temperature given, or what is the temperature taken, humidity, pressure, catalyst, or any other environmental aspects are being there means we couldn't able to get to know from just equation only until and unless we mention them separately. So these are some of the limitations of the chemical equations. In the types of chemical reactions, let us discuss the first one, that is combination reaction. One element or one compound reacts with another element or compound to produce only single compound to the right side. So these kind of reactions are called as combination reactions. Two reactants will be there and only one product will be there. For example, the first magnesium ribbon experiment, if we take magnesium reacting with oxygen to produce magnesium oxide, here reactants are two whereas the product is only one. Otherwise, carbon, when it reacts with oxygen, we are going to get the carbon dioxide. Here reactants are two whereas the product is only one. Otherwise, hydrogen gas, when it reacts with oxygen gas, we are going to get water. Here reactants are two whereas the product is one. If the reactants are two and the product is only one, that kind of reaction is called as combination reaction. Let us check one more then. The next kind of reaction is decomposition reaction. The name itself is decomposition. It means splitting into more than one. One reactant will be there. If we are supplying some energy to this one, it will be dislocated into two products. So one reactant and two products. Let us take one example. Calcium carbonate, CaCO3. Upon heating, it produces calcium oxide and carbon dioxide. So CaCO3 in the presence of heat decomposes to calcium oxide and carbon dioxide. Let us take one more then. Silver chloride in the presence of sunlight. Silver chloride in the presence of sunlight, it is going to give us silver and chloride. Next one. Water in the presence of electricity. This process is called as electrolysis. So in the process of electrolysis, water gives us hydrogen gas and oxygen gas. So now in all these three cases, reactants are only one whereas the products are two. Only one reactant is giving two products. That kind of reactions are called as decomposition reaction. Next reaction is displacement reaction. Let us take the previous. What will happen in this is, one element or one compound will react with the another element or compound, and this one is going to replace one element or one ion from this, that is AC, and that released one will be separated. So A plus BC gives AC plus B. Let us take one example so that you will understand clearly. Zinc, when it reacts with sulfuric acid, zinc is more reactive than hydrogen, so it displaces hydrogen. Then we will get ZnSO4 and hydrogen gas. So this kind of reactions are called as displacement reactions. Double displacement reaction. In this, what happens means, if we have two compounds AB plus CD, A will displaces the C, so it will get AD plus these two will form another compound, so it will be BC, AD plus BC. Let us take with one example now. Sodium chloride, I am making it react with sulfuric acid. NaCl plus H2SO4 gives rise sodium hydrogen sulfate plus HCl we are going to get. Otherwise, sodium chloride I am reacting it with silver nitrate. Then what happens here is, this Ag reacts with this Cl, so we will get silver chloride, plus this Na reacts with this NO3, so we will get sodium nitrate, NaNO3. So these kind of reactions are called as double displacement reactions. Take an example of magnesium reacting with oxygen to produce magnesium oxide. Now in the beginning, if we check the reactants, here we have magnesium alone. Now after the reaction we got magnesium oxide. So it means for this magnesium, oxygen is being added. Whenever in any reaction if oxygen is added, that is called as oxidation. Let us take the same example. Mg plus O2 gives rise MgO. Mg plus O2 gives rise MgO. In the reactant side, if I observe the oxygen, two atoms are there. In the product, if I observe the oxygen, it is only single atom. So here, where the oxygens are deleted or removed is called as reduction. Oxygen is added means oxidation. If oxygen is removed or deleted means reduction. In any equation, if these two are combinedly there, then that kind of reactions are called as redox reactions. Let us check this with same example. Magnesium plus oxygen gives rise magnesium oxide. Here Mg is being oxidized. Oxygen from O2 to O, it is being reduced. So oxidation is there in this only, reduction is also there in this only. So this kind of reaction is called as redox reaction. Let us discuss about the corrosion. A metal due to the atmospheric conditions or else due to any chemicals, the top layer of that metal will be eaten away. That is called as corrosion. Actually, this corrosion is a process by which a metal reacts with oxygen or water vapor or water or else chemicals to form a colored layer on the top of it. Then that is called as corrosion. So in this corrosion we will discuss about two metals. One is iron and one is copper. This corrosion of iron is particularly called as rusting. Coming to this, iron we know very well. Iron, when it reacts with oxygen, we will get either FeO or else either Fe2O3, either Fe3O4. So this, whether it is forming FeO or Fe2O3 or Fe3O4, it will be decided by the availability of oxygen and the pressure which is acting upon it. Now moving to this copper. Copper, when it reacts with substances like carbon dioxide which is present in the atmosphere, or else sulfur trioxide which is present in the atmosphere, or else water which is present in the atmosphere, it changes to other color which is blue color or else green color. So when it is forming into a blue color, that means a blue color layer will form upon this one, that is called as malachite, that is MALACHITE. And when it is forming green color on the top, then that compound is called as brochantite. Then how we are going to prevent this corrosion means, first one is we need to use a protective coating, it applying like a paint or keeping any powder on the top of it, or coating it with a plastic or covering it with plastic, or else wax. So these all what they are going to do is they will act like barriers so that the metal, the original metal, won't react with the atmosphere which is outside. And next one is adding grease or oil also works out. It is also doing the same case. And the next one is the process galvanization. Iron metal will be completely dipped in the zinc molten liquid. Zinc will be heated so much so that it will become melt completely, so that is molten state. Now this iron is going to be dipped into this molten state, so iron article completely covered with zinc on the top. Now whenever this item is being exposed to the atmosphere, the outer layer zinc is going to be eaten away, whereas this iron will be in safe side. So where the zinc layer will be coated on the iron, the process is called as galvanization. And the next one is about rancidity. Actually, so many food items will contain fats or oils. And these fats and oils, whenever they are exposed to the oxygen, that is nothing but oxidized, they gives us bad smell or bad taste. That change is called as rancidity. Then how we are going to prevent this rancidity? First one is we need to store the food items in airtight containers. Obviously, this slows down the process of this rancidification. Next, keeping it in the refrigerator or fridge, simply refrigeration method slows down the rancidification. Next one is antioxidants we will use. So this antioxidants, what they will do is they will prevent the oxidation to further happen. Next one is we know very well about this chips. Chips will be filled with another gas, not with the oxygen. So normally they will flushed with the nitrogen gas. They are flushed with the nitrogen gas so that it replaces the complete oxygen gas, so that it won't be oxidized further. Next one is storing away from the direct sunlights.